Welcome all. I am Professor Tamal Mandal, Department of Chemical Engineering, National Institute of Technology, Durgapur. Today, I am delivering a lecture on conduction heat transfer, and this is from basically the role of chemical engineer to produce the useful materials for the mankinds, and basically the process engineering also do the same. And whenever we are going for the any transformation of materials for production of new materials by chemical and biochemical reaction may cause of heat generation or depletion due to the formation of new bond and the destruction of the old bonds. So, extraction of heat and supply of heat is required to maintain the optimum temperature for the optimal productivity. In this case, reaction rate constant increase with the increasing temperature, but in a certain level of temperature means the optimum temperature is required for the maximum productivity. And if we take a very small simple example that if we take the some raw materials, the reactant materials into a conical flask or beaker or in a test tube, for the reaction, and with the time of reaction it will for either produce the heat or it will it will deplete the heat from the system. So, for this when the deplete of heat from the system is called the endothermic reaction, and in this case heat will be supplied from the environment to the system to maintain the temperature, and from the for exothermic reaction heat will be produced, and that will be passed to the surroundings to maintain its temperature based on the temperature difference from system to surroundings. But in chemical industry, when we are handling a huge amount of materials, almost 10 to the power 3 to 10 to the power 5 times more and even more materials, and then the production of heat or the depletion of heat in such a quantity that we cannot maintain that with the either supplying heat from the environment or to the environment. So, then it is very much required to some device design for either supply of heat for the endothermic reaction and for the extraction of heat from the exothermic reaction. So, if any reactions occur in a exothermic reaction, then cold water in a jacket system normally it is passed, and the cold water can extract the heat from the system to give a maintain of heat in the system for better productivity. And similarly, for endothermic reaction, the temperature fall due to the depletion of heat, and then this heat can be supplied by steam through the coil system or the jacket system. So, here if we see that the we maintain a agitator with a uniform velocity to maintain the uniformity of the reactors for heat transfer, mass transfer and the momentum transfer point of view. So, this case agitators when it is rotating into the system, so it also produce some heat due to the its speed and its frictional force to the liquid. So, in these types of system we would like to see that the three types of heat transfer normally occur, and when the system is working, then from the fluid of the system, it is the fluid is getting heated due to the exothermic reaction. So, then heat will be transferred from the bulk fluid to the wall side, and that will be the convection mode, and then from reactor wall in wall is solid medium, and that is the heat transfer from hot wall to the cold wall side is the conduction. And another types of heat transfer is the radiation heat transfer, which is normally can be considered as a source term in this case. So, then it can be pictorially present in that way that the hot fluid is transmitting heat to the wall, solid wall, or I means here the reactor wall, and from that reactor wall to it is going to the cold fluid, which is used as a coolant for this case. Or in opposite way, it can be if it is the heat depletion, means the endothermic reaction. So, the high hot fluid has to be passed from the jacket system or the coil system. So, then the heat will be supplied by this hot fluid to the system. So, basically this two fluid and one solid is here. So, one side is the conduction in the solid wall and the two side is the liquid. Here the convection heat transfer is observed. And then the convection will occur, and then the heat will be extracted by the cold fluid. So, the hot fluid will donating the heat to the cold fluid, and that the initial and final temperature can be measured by MCP2 M2CP2 Ti minus Tf. Similarly, for the heat conduction at the solid layer can be used by the equation Q equals to minus Ka dt dx, and for the other fluid when this is the cold fluid is getting the heat. So, that heat will be a help to increase the temperature of the cold fluid from initial to final. It is denoted as Ti is the initial and Tf is the final temperature. Here the phenomenological law governing the transfer of energy by molecular diffusion Fourier's law is presented, and heat flux and the energy equation for solid system are expanded in rectangular, cylindrical and spherical coordinates. So, if we now consider that the how Fourier's law can be expressed. So, in this case we will consider that the two plate within that two plate some solid or liquid or gas may be present, and that the one plate will be maintained at a temperature Th and the lower plate is maintained at a temperature T equals to 0. Now, the heat transfer will start it from higher temperature to lower temperature due to the temperature difference, and for the conduction heat transfer the initial adjacent layer of the hot plate will get first heated and it will start to vibrate, and this vibrational energy transferred to the next layer and next layer, that so on. So, ultimately initial stage the temperature profile will be parabolic and hyperabolic in nature, that is the unsteady state condition, but in a steady state condition we will get a straight line like this, and that will be at that moment the amount of heat transfer from top layer to the next layer and next to next will be the same, means the every layer heat transfer will be the constant for the steady state conduction. And from this we know that the as Q is the heat transfer per unit area will be depends on the directly proportional to the temperature difference Th minus T0, and it will be inversely proportional to the distance of the two plates. So, this can be modified in this fashion that the Q by A proportional to delta T versus delta Z is the delta Z is now considered in the direction of the heat flow, and another is that the difference term can be removed to a differential equation, that the Q by A proportional to dt by dz, and now we can equation we can form that the Q by A equals to minus K dt dz. Here K is the thermal conductivity. Thermal conductivity depends on the which material through which the heat is transferring from hot zone to the colder zone. So, this is the one dimensional equations. In this case, it is written q z means the where the heat transfer in the direction of the z direction, k is defined as the thermal conductivity, and as it is the property of fluid and usually evaluated by the experiment. So, the in this equation the negative sign is given here. This is due to the when the temperature is going from the higher zone to the lower zone. So, that is the gradient of temperature is negative. So, the equation it is used the minus sign, and this above analysis has been presented rather in simple system. Generally, fluid will possess 3 temperature gradients with corresponding heat flux components in a given coordinate system. When this is the case, 3 heat flux terms q x, q y and q z will be there, and in this case we can write in the fashion q x equals to minus k dt dx, q y in the y direction minus k dt dy, and q z equals to minus k dt dz in the based on the x y z direction, and this can be presented in a vector form that the q equals to delta 1 is the unit vector for the x direction, q x plus delta 2 is the unit vector for the y direction, and the q y plus del 3 is the unit vector in the z direction into q z. So, this can be presented in this fashion that the minus delta 1 k dt dx plus delta 2 k dt dy plus delta 3 k dt dz equals to minus k delta t. So, the term that will be frequently employed in the text in this thermal diffusivity is another important term is written as a square fashion, that is thermal conductivity by specific heat and the density of the material. So, all components of the heat flux vector q in a given coordinate system can be expressed in terms of the thermal conductivity of the fluid and a temperature gradient. These are presented in table 1 for rectangular, cylindrical and spherical coordinates. The equations are applicable to all fluids obeying the Fourier's law. So, these are the table 1 the presented for rectangular coordinates, for cylindrical coordinates and for the spherical coordinates. Now, thermal conductivity. Thermal conductivity is normally considered it is constant, but it is not exactly constant. Sometimes it depends on the temperature. So, this can be equation thermal k equals to A plus B T. The thermal conductivity of metals is generally nearly constant or decreases slightly as the temperature is increased, and the conductivity of alloys is less than the pure metal. So, in other cases it is observed that glass and the most non-porous materials, the thermal conductivities are much lower from about 0.35 to 0.3.5 watt per meter degree centigrade, and that is why these materials are sometimes used as a insulator materials. In liquid, K decreases with temperature, but water is an exception with K value 0.5 to 0.7 watt per meter degree centigrade, and K goes through a maximum as the temperature is raised. Glasses have thermal conductivities an order of magnitude lower than those for liquids, and with increasing the temperature gases the K value increases, but very little effect of thermal conductivity for the gases in case of the pressure, and after 10 bar some little effect is normally observed for the gases. Now, the steady state conduction. Here the steady state conduction is the form of conduction that happens when the temperature difference is the driving force in conduction are constant. so that the spatial distribution of temperature in the conducting object does not change any further. So, these equation q by A equals to minus k dt dx and dt equals to minus q by k dx, in this fashion we can present, and q by A equals to k if we integrate this equation and put the dimensions, put the limits from the T1 to T2 and from the x1 to x2, and the minus value is here adjusted. So, T1 minus T2, x2 minus x1. So, this thermal flux is nothing but k delta T by B is the thickness of the material is presented here. So, a simple illustration here, a layer of pulverized rock 6 inch thick is used as a layer of thermal insulation in a flat wall. The temperature, the cold side of the cork is 40 degree Fahrenheit and that the warm side is 180 degree Fahrenheit. The thermal conductivity of the cork at 32 degree Fahrenheit is 0.021 BTU per feet per hour degree Fahrenheit, and that at 200 degree Fahrenheit is 0.032. The area of the wall is 25 feet square. So, what is the rate of heat flow through the wall in BTU per hour? So, the arithmetic average temperature of the cork layer is 40 plus 180 by 2, that is 110 degree Fahrenheit. By linear interpolation, the thermal conductivity at 110 degree Fahrenheit will be k equals to, this is the 0.021 at it is after that the temperature rise up. So, for 200 to 200 minus 32 means that is the 168 temperature change, the thermal conductivity change occurred actually 0.32 minus 0.021, that is 0.11, and so per unit degree of temperature difference it is coming this and multiplied by the 100 degree 110 degree minus 32. So, the total thermal conductivity change is coming like this, that is the 0.026 BTU per hour per feet per degree Fahrenheit, and area is given here 25 feet square. Delta T is the coming 180 and minus 40 degree Fahrenheit. So, this is on 40 degree Fahrenheit and thickness B is the 6 inch. So, this is 0.5 feet. So, putting it into the equation it is coming that the 182 BTU per hour. So, then for the layer of composite layer of different materials are used for the insulation. So, in this case the temperature gradients are the what will be the thermal flux for every material will be same at the steady state condition, but that is nothing but due to not the how much per unit area it will be passed, that depends on the temperature gradient in the different zone. So, this is in first case the temperature, how much heat is flowing from hot fluid to the first zone means here is the B A is the thickness and delta T is the temperature difference, and what that depends on the thermal conductivity of first layer of insulation. But in next case when this is the second layer that is the R B in the form of, that is what will be the thermal conductivity of that. So, initially how much heat is transmitting from the first layer, that much may not be transferred from second layer. So, little accumulation will takes place in this zone, and for that the temperature gradient will fall and the heat flow will be reduced for the first layer, and similarly for the second layer how much heat is transmitting to the third layer. So, based on the third layer thermal conductivity, that the heat will be dissipated from there, and if the third layer thermal conductivity is lesser than second layer. So, then this case the some more heat will be accumulated in this junction of the second layer and third layer, and then the some heat will be accumulated. So, due to that some temperature will rise here. So, the temperature gradient will be reduced. So, the heat flow will be reduced from the second layer too. So, this way the total effect will come and the temperature gradient for the different section will be different, but the total heat loss from this first layer to second layer and second layer to third layer will be the same. So, now if we go for the steady state heat transfer through a cylindrical shape geometry, then from this basic equation Q by A equals to minus K dt dr. So, in this case 2 pi R L is the area, and area is variable for the cylindrical shape. So, then the separation of the variables we can see that we can r dr by r from the r I means the inner radius to the outer radius r 0, and the temperature inner side temperature to outer side temperature T 0 to T I to T 0, but here minus sign is has been managed with here. So, T 0 to T I has been taken the limit, and from this we can get after integration that Q is coming to pi K L into T I minus T 0 by ln R 0 by R I. Similarly, for others geometry we can calculate the overall heat transfer coefficient in overall heat transfer in a steady state condition. It is another illustrations is a tube of 60 millimeter OD and is insulated with a 50 millimeter layer of silica foam, for which the conductivity is 0.055 watt per meter degree centigrade, followed with a 40 millimeter layer of cork with a conductivity of 0.05 watt per meter degree centigrade. If the temperature of the outer surface of the pipe is 150 degree centigrade and the temperature of the outer surface of the cork is 30 degree centigrade, then we have to calculate the heat loss in watt per meter of the pipe. These layers are too thick to use the arithmetic mean radius, and the logarithmic mean radius should be used. For the silica layer, it is coming 80 minus 30, 80 is the 50 millimeter, and the radius here is the 60 by 2, that is 30. So, 30 plus 50 80 minus 30 by ln 80 by 30. So, it is coming 50.97 millimeter, and for the cork layer it is coming 30, it is diameter is given 60 millimeter. So, this is radius is the 30 millimeter, and layer of silica is the 50. So, 30 plus 50 80, and another layer is it is given 40 millimeter. So, from there it is coming 120 millimeter minus 80. So, this way it is calculation is coming the R L equals to 98.64 millimeter. So, from there if we now directly put into the equation Q A K A T I minus T x, and T x is the junction temperature and by x is the thickness, k b by into a b T x minus T 0 by x b. So, where T x is the temperature at the interface between the silica and the cork, and then if we put that the area equals to is coming 2 pi r l are already calculated. So, this much value and a b is coming this. So, next if we put that, so the q a equals to this, and in this putting the equation, the thermal conductivity equation, and q b equals to this. So, now at the steady state condition, so q a or q b both are same. So, now we can if we use this equation, two equations, and after adding these two, we are getting the T x and T x will be cancelled out, and from there q by L will come 29.1 watt per meter. So, in the case of spherical shape, we can put the equations in the form of in this in this form. You have 4 q equals to k dt dr. In this case 4 pi r square will be the spherical area. So, from there we can calculate also radius r I to r 0 and dr I by r square form, and similarly for this case we can calculate total q value in this way. Similar fashion we can calculate the spherical shape geometry also. So, that is all. Thank you very much.